Hello everyone, today I'm going to talk about the utilization of invasive species, Sitka spruce, for the economic benefit of the human. So this is my following statement. Picea sitchensis is the most common plantation species in northwest Europe and is considered as an invasive species in Norway as in 2012. Despite that Picea sitchensis is an invasive species, but it has a significant importance in forestry for timber production that has huge application in different industries. This study is aimed to investigate the economic benefits of Picea sitchensis to humans. Invasive species is a non-native species that spread from other habitats and usually bring more harms than benefit to the original habitats. Picea sitchensis is a large coniferous evergreen tree that is native to the west coast of North America. Picea sitchensis is the largest sprout and live a long life as tree, usually more than 800 years. It can achieve the height 65 meters. Sitka spruce grow best on sites with deep, moist, well-drained soil, but it also displays great tolerance towards salty beaches and deep brackish water. That is why they are such a good invasive species. Do keep in mind that this species does not appear in Asia at all, only it will appear in Europe. Today we are using two research papers to review. First, let us talk about methodology of research done by Sean 2008. In the experiment site, there was a standard square spacing of 1.83 meters and there were 3 complete replications each treatment. So 4 representative families were selected. Family 1 is Queen Charlotte Island, QCI control. The other 3 families are with their own characteristic. 12 trees of 18 cm DPH or greater were randomly selected across each replicate to represent potential solid tree, making a total of 36 trees fail per treatment. Figure 1 shows that the tree selected for failing and more detailed analysis within one of the chosen treatments. The select tree will fail and measure for diameter and the number of points along the length of the pole to allow estimation of stem volume. The number and diameter of each branch on the outer surface of the log were measured to allow the knot to surface area ratio to be estimated. Let's refer to Figure 2. Figure 2 measuring the diameter of a selected tree. This was done at the number of points along the length of the stem to calculate volume. Each felled tree will visually assess for optimal green log volume according to Forestry Commission guidance prior to cutting to a standard log size of 3.1 meter. All logs were transported to a sawmill for processing, where they were cut into standard timber lengths, known as batten. The batten was randomly divided into 2 samples. One was tested at the strength class C16 and one at C24. Timber graded at C16 is used for general construction work and partial load bearing end users such as wall strut or framework. Second, let us talk about the methodology of research done by Henry in 2010. All crops will be planted as a 50-50 mixture of improved and unimproved material, either as an intimate or line mixture. The level of improvement is estimated to be a 50% increase in volume, which is approximately equivalent to 1 yield class increase in wood production on the yield class 14 site. An increase of 1 yield class is assumed for all sites. 400 to 600 trees per hectare will provide the final crop volume. This is the result from the first journal. Family 2 had 42% additional green log volume, while Family 3 had 39% relative to the QCI control. The costs for the improved progeny were all lower than the QCI control. When the random selection of pattern from each family were tested against the C16 reject grading criteria, all of the length from all families passed and none were rejected. When the second random sample of length from each family were tested against the C24 reject grading criteria, there was a lower overall pass rate varying from 50% in Family 4 to 74% in Family 2, with the QCI control having a pass rate of 70%. However, the difference between families were not statistically significant. In general terms of site productivity, the trial in Kershaw Forest was on a good quality site. The QCI family and Family 4 were predicted to be growing at yield class 22, and the faster growing Family 2 and 3 were predicted to be growing at yield class 24. As expected, Family 4 had the highest wood density as measured using the Pickering gun, and Family 2 had the lowest wood density. The QCI 3 and Family 3 had similar wood density, which was significantly higher than Family 2 but lower than Family 4. Grain angle were used to measure the mean straightness score. All three of the improved family were on an average stricter than the QCI. Keep in mind that lower basal area equal to lower number of surviving tree per hectare. All improved family had higher number of surviving tree per hectare than the unimproved QCI. All improved family show increase in both green log volume and batten volume per hectare compared to the QCI control. This table shows the comparison of the effect of an increase of 1 U class across a range of U class 14 to 24. The trend shows that the higher the U class, the higher the discounted revenue and benefits. The use of improved Sitka spruce will increase the current value of the crop on average by about €987 per hectare. This table shows the detailed cost comparison of 100% unimproved Washington Sitka spruce against 50-50 mixture of improved unimproved Washington Sitka spruce. The most important information is that 50-50 mixture of improved unimproved Washington Sitka spruce costs €156 per hectare compared to the 100% unimproved Sitka spruce. Table 3 shows the cost-benefit ratio of planting improved Washington Sitka spruce picture. Cost-benefit ratio increased with the increase in U class, with the exception of U plus 52, which has a 1/6.2 ratio. The result of this study indicates that the improved Sitka spruce can produce increased volume of sawlogs and saw timber with no decrease in the pass rate C16 or C24 string classes. Comparing the result with standard yield timber, I suggest that it is very close to what would be expected. The reason for that large increase in saw timber from green log on a per hectare basis is a combination of increased green log volume from individual trees because they are stricter, the lower mortality rate in the improved family and a larger average tree diameter, so that a greater percentage of trees are able to potentially produce saw timber. Wood density as measured by the Pilodin appear to have no effect on the pass rate of the saw timber, as family 4, which had the highest density, also had the lowest pass rate as C24, which is 62%, although the difference between the family were not significant. Increase of a green log volume of up to 42% at an individual tree level and 135 level on a per hectare basis were measured of the strictest, fast-growing family. It appeared that the improved straightness and lighter branching in family 2 compensated for the reduced wood density, resulting in the highest pass rate, which is 74%, as the previous study has suggested. There is significant benefits for increasing the productivity of lower yield class sites. However, for higher yield class sites, the increase in productivity will result in shorter rotation that will contain higher percentage of juvenile woods with poorer wood properties. Below is the assumption that will be taken into the calculation. Because of planting 50% of the crop with improved Washington Sitka spruce is more than offset by the increased benefit per hectare as shown in Table 1. Combining the benefit from Table 1 with the additional cost from Table 2, this allowed the examination of the net impact of using improved planting stock. The cost-benefit ratio is an impressive 1/6.3, which, even in times of budgetary limitation, make economic sense to invest. By comparing the result with previous study, it is expected that the use of improved Washington Sitka spruce will increase the profit significantly relative to 100% unimproved plant stock. This study has demonstrated that improved Sitka spruce can offer substantial increase in the volume of green log and sawn timber produced at an individual tree level, but particularly at the per hectare level at close to rotation age, relative to unimproved QCI material. This increase in volume is obtained with no significant difference in strain grading pass rate at the sawmill, meaning that the improved material is at least comparable to unimproved QCI in terms of sustainability for construction rates. For an additional €156 per hectare, the resulting increase in volume is worth on average €987 per hectare. Thus, even under extremely conservative assumptions, the planting of improved Washington Sitka spruce in Ireland will more than cover the additional cost of the planting material. It will also increase the productivity of the national forest investment. Concern about the higher cost of improved Washington plant should not dissuade forest owners from using this material.